Okay, so before we can construct a confidence interval for our population parameter p, we need to check three conditions. These are the random, 10%, and large counts condition. The random condition says that the data needs to come from a well-designed random sample or a randomized experiment. The 10% condition says that when you're sampling without replacement, you need to make sure that you take no more than 10% of the population. So in other words, your sample size is less than or equal to 1/10 of your population size, large N. And the large counts condition says that both n times p hat and n times 1 minus p hat are at least 10. We can also call this the number of successes and the number of successes and failures, and I'm going to talk about this later on. So what happens if if we don't meet any of these conditions? So let's look at first the violation of the random condition. If we don't have a random sample, that's probably the worst thing you could do when you're doing studies in statistics. It essentially becomes pointless, to infer anything about the population, because people can claim, reasonably so, that your sample is biased. So it becomes pointless to make a confidence interval. For example, let's say that I was trying to figure out what proportion of the population watches at least, one sports game per week. And let's say I go to the basketball courts one night, and I survey 30 of the people there, and 90% of them, watch, at least one sports game per week. I can't say, oh, okay, then that means that probably 90% of the population watches at least one sports game per week. We know that we intuitively know that that's unreasonable to claim, because the people that play basketball at the courts, probably are more into sports than the average person. They're there playing sports, so they're probably going to watch sports, when on their free time as well. So it would not be reasonable for me to, make that claim. So this is one of the most important conditions. So you want to always avoid, getting convenience samples or bias samples. You always want to meet this condition. Okay, so what happens when we violate the large counts condition? Okay, so this goes back to the previous unit when we learned about sampling distributions. And what we discovered was that the sampling distribution for p hat will be approximately normal when we have certain combinations of values for the sample size and the population or the proportion value. We found that it was good to have a proportion value closer to 0.5, and it's good to have a larger sample size. And we came up with this rule that okay, when we take we want their products to be at least 10. When it is, we're more likely to get a sample distribution that will be about normal. Because if it's not normal, since our confidence interval depends on the normal curve, we couldn't make one, because it depends on it being normal, and it being normal depends on this. So it's actually going to end up having a lower capture rate. So if we said that the confidence interval was going to be 95%, it would actually have a capture rate lower than 95%. So it'd be kind of like false advertising. All right, now the 10% condition. So what happens when we violate the 10% condition? This one's kind of weird to talk about or think about, but what happens is that your standard deviation actually becomes inaccurate. The formula that we use leads to an inaccurate standard deviation value. And again, it's kind of weird to think about, because you'd be like, well, isn't it better to take a bigger sample size? Why would we want to have a sample size less than 10% of the population? Well, you're not wrong for thinking that. Like that's fine. It's just that we're going to need a different formula for the standard deviation. So if we violate this condition, our confidence intervals will actually be larger than usual, because we're going to get standard deviation values that are bigger. And we're actually going to end up having higher capture rate than we advertise. If you take more advanced statistics course, you're actually probably going to learn about the standard correction error, and that's going to be when you actually take sample sizes more than 10%. But that's usually going to be something in second or third year statistics course. Okay, so now let's look at the confidence interval that we're going to make for the population proportion P. So when we meet these conditions, we can then say the sample distribution of P hat will be approximately normal. We know it's going to have a mean of the population proportion because it's an unbiased estimator, and a standard deviation will be equal to the square root of P times 1 minus P over N. This is what we learned in the previous chapter. And earlier we figured out that our confidence interval will have this form where we start with our statistic, or we call this our point estimate, and from there we add and subtract a margin of error, or the critical value times the standard deviation of the statistic. And we're going to break this down in more detail in the next problem. But for now, let's analyze this. If we recall, our population, proportion is P, and we need that in order to come up with our standard deviation value. But if we know the population proportion, we're not going to do a study because we know what it is. So we're only going to do a study if we don't know what the population proportion is. But if we don't know what it is, then we can't do this formula. So what happens is that we're going to make an adjustment to this formula. This formula is going to actually just be replaced with P hat. And when it's replaced with P hat, since it's technically an estimate of the population standard deviation, we call it the standard error. So we call it the standard error of the sample proportion P hat, because again, it's an estimate of the population standard deviation. So it would technically be wrong to name it that. So that's all that is. So essentially means the same thing as standard deviation. It's just referring, to this technicality where we use P hat instead of P. So formally, you're going to hear the word standard error basically probably for the rest of your course in statistics. So just make sure you recognize that difference. It is important, but it really won't cause too much confusion in your calculations. Okay, so now let's look at how we actually make a confidence interval by first figuring out how we can find the critical values. So if you want to find the critical values for a 96% confidence interval, let's just draw a picture to see what we're doing. We're looking at essentially a normal curve where 96% of the area is captured. We're looking for, looking at this normal curve where we have 96% of the area, and we're essentially just trying to find the boundary points. Like how many standard deviations away is the left boundary? We're going to call this negative z star. And how many standard deviations away is the right boundary? We're going to call this just z star. How far away are they from the center? And for this, we just can refer to our normal table, or we can use technology because this is just a normal distribution with a mean of 0 and a standard deviation of 1. So you're using just some logic. If this is 96%, we know that there's 4% left over. So there's 2% to the right and 2% to the left. So when we're looking at our normal table for this z star value, let me go ahead and pop it out. Your normal table will tell you what the area is to the left. So we're going to look for when the area is 2% or 0.02. And that'll give us our negative z star value. Likewise, we can look to when it's 0.98, because 0.98 to the left of this z star value will be the same. It's critical value, but just in a positive, just being positive. So Going in here, we find something that's as close to 0.02 as we can find. And this is as close as we can get, 0.0202. This is saying that there's 0.0202 area to the left. This is as close as we can get to, 0.02, and we find the z value associated with that. It's going to be negative 2.05. So this is going to be negative 2.05, and this side will be positive 2.05. The typical answer will be that the z star will be a positive quantity, so our answer will be this, 2.05.